Hey, what's up guys? In this video we are going to be revisiting the auto filter. This is the advanced look at the auto filter, and let's jump into it. It's one of those important devices that we're going to be working with in our journey. So this is a refresher, I guess. So you got the filter, you got the resonance. Okay, that's the refresher. We should basically understand what a filter does. Does cool stuff like that. This is a low pass filter, right? It lets the low stuff pass through. We can confirm, right? There's also high pass. Does some cool stuff like that. We got our notch, we got our band pass. We got a resonance, which gives it a boost at the cutoff points, and all of that fun stuff. And this is really cool. And back in the day, before we had all the awesome, CPUs and processing power, I would use the auto filter because it was optimized for live. I would have it set to the filter frequency around 100, and I would boost the resonance. And this would give me a little bit of low end in my kicks, which is kind of, I guess, like a tape bump, maybe like a 12 dB per octave. Right? Just to give it low end. That's muddy, but whatever. You get the idea. This is how I would use it, and it was really great. And something happened. Things changed in, why'd I close that? Things changed in, I don't know what year it was, 2013? Ableton Live 8 was released. I think it was Ableton Live 8. And it released, or it just did an overhaul of all of the filters, right? Made the EQ more clean and things like that. And, made it SSE2 optimized. It didn't sound like crap anymore. You could do something cool called oversampling, which gives it kind of more resolution and all that sort of fun stuff, and gives just more quality. It became mastering grade, very high quality EQ, and a lot of the filters, right? The auto filter, and then the filter in analog and sampler and simpler, they all got the same kind of overhaul. The filter got just a boost in quality. And beyond that, they introduced some analog modeled filters. So what the heck is that? It scares me. Don't be scared. I'm gonna buckle myself in so we can kind of explain this. So we're looking at the circuit type drop down menu right here. Right now it's clean, right? And then we have OSR, MS2, SMP, PRT. What are these? We're going to find out. But clean is clean. Okay, so how filters work is they use, I guess, recursive algebra, and there's delays and feedback and all sorts of wacky stuff that goes into filter design. And I'm not gonna start explaining digital filters, but it's super duper clean. They're mathematically very accurate across all frequencies and across a certain resonance here at 9.44 kilohertz will be the same resonance at 472 hertz. It's mathematically sound and consistent, and it sounds clean. And an analog filter, which is something with circuitry. Do I have one? I don't actually have one. I'm like immediately grabbable, but there is a synth behind me, but I won't be able to show you. There's like circuitry within them. Here's a development board. It has like the MIDI stuff in there, but there's circuitry over here, right? And this is for the audio output. There's filters in here, and this is it's a piece of hardware. It's an analog, like it makes electricity, and it's not ones and zeros. It's actually like a discrete kind of signal besides the DSP, but then it's converted to analog. So that's what we're looking at. We're looking at the difference between digital ones and zeros and then analog, which is electricity over time, right? So a clean filter it performs way better than any analog filter could ever hope to achieve. No noise. Well, it doesn't. There is noise, but it's a different kind of noise. Like, it just doesn't have to compensate. It's perfectly aligned. It's just like floating point math, algebra. Really cool, and that's clean. But it doesn't have the characteristics that, like, the thing that analog stuff does, how it behaves, is actually pleasing to the ear. It's familiar. It adds something to the sound. It's not transparent. And what happens when you want to add analog stuff, analog modeled filters? What do? Who do you ask? Well, you get cytomic on the case. And this is the drop, and this is what a lot of the filters in Ableton Live were designed by him and implemented. Not all of them. I'll actually show you what the drop looks like in a VST here. The drop right there. So this is the drop right here, and this might look familiar, right? We have the filter, low pass frequency here, resonance, all that fun stuff. Then we have all of these things here. So some of these will look familiar, MS2, right? Not all of them are in there, but yeah, if you're considering getting some like really powerful filters, check out the drop. But that's for a different topic, right? We're not quite there yet. So Andrew Simper, he basically optimized, as far as I know, if memory serves correctly, he optimized the EQ8 filters, made them SSE2, brought in his expertise in filter design, and helped the team make some really high quality filters. So made them clean, and then added some analog modeled ones here. So OSR, MS2, SMP, and PRD. Let's actually just click on one and see what's going on here. Whoa, what's that? Drive, what does that mean? Right? So we have to kind of go over the topology of how an analog filter behaves and how people would kind of manipulate the filter. So I'm going to bust out the pen, and let's see. This is color good. Yeah, it is. So let's say we have. I'm just going to draw out kind of an abstract synth here, right? We should all know this. We have a signal here, right? And this would be signal, and then that essentially goes into the filter, right? Goes into the filter, and I'll just name that, and then that goes into the out. And then that, will go into a loudspeaker or something, right? My loudspeaker, and then it'll go into an ear. That's a weird looking ear, but that's an ear. So there's that. Do, right? So what is drive? Well, at this stage, if we take this signal and we up the volume, right? We add more gain, right? We will overdrive the filter, right? So we'll have this go out like that. So instead of that, it will just, go into the filter that way. So yeah, we're giving it lots of gain. Holy crap. And what that does is that will overdrive, or you'll hear the terms OD, overdrive, and that's in the filter. So what happens when you overdrive a filter? It will be able to handle what you're putting into it, but it will affect the sound. Like it won't be able to it'll be like, I can handle this, but I'm going to shake a little bit, and I'm going to add some imperfections. And that's essentially what the drive is doing. We're essentially adding more gain, boosting it, and that's being fed into the filter. And when you do that, well, you get more volume, but then it adds, this I'll use the term. We use the term warmth, analog warmth, right? Tape or vinyl, right? That spinny disc thing. It looks provocative. Like vinyl, right? I don't need to show you what vinyl is, but vinyl, there's so much going on, and it was mastered in such a way, and then it goes through a needle, through a thing, but before it goes through a needle, it's on like this wavy plastic thing, and then it goes up, and then it's amplified, a very weak signal. It's amplified a whole lot, and then it goes into speaker. It's like all these stages of adding kind of color to it. And that's what we enjoy hearing. So that is the drive. It's drive, but what it is it's essentially it's just having a utility and it just boosting the gain. It's basically the exact same thing, but it will kind of color the sound as opposed to clean, which is mathematically, accurate for being super duper clean. But when you have a signal that if you have something digital and you clip, it will essentially, roll it off on the top end. It's not a very pleasing kind of drive sound. But you don't really need to worry about that within live. There's a lot of headroom. You'd have to work really hard to get digital clipping in there, but that's essentially the idea. So let's give it a listen here. Right, and we can hear maybe the resonance. That resonance part is a lot different now. Right, that's pretty clean. Right, what happened there? Well, that smudged it a little bit. Not so clean anymore, is it? But it sounds a little bit more pleasing, a lot more natural, a lot more familiar, and that is essentially, what what that is. And if we add some drive, right, we boost the overall volume or gain of the signal, but it kind of smudges it a little bit more. And that's essentially the appealing nature of these analog modeled filters, because you can kind of abuse them and they will create a really pleasing sound. And we've been doing this since the 50s, right? It's like the Marshall amps, just boosting them to all hell, and they can't handle, so they have all this coloration, but then we like it, right? It sounds awesome. Similar thing here. I want to point out another concept. You'll come across with a lot of analog modeled filter devices, plugins, things like that. Right, we have the signal, right? And then that signal is boosted, right? The gain is boosted, and that's being fed into the filter. And then that is overdriving the filter. And then that goes out and then to the ear. There is another one, right? So this is overdrive, right? This whole diagram here is overdrive. There's another one, right? So a lot of synths, they have an external filter input, right? And you'd have your external filter input like so, and then you'd have like a guitar that goes. That's weird looking guitar, but yeah, there's a guitar goes into the filter. You can have external things and filter them. You can also, with CV and stuff, you can have a completely other synth. Weird synth, but yeah, right? And that can go into the filter here, and you can have access to that filter. Really cool, and that is all well and good, but what you would do is you'd have the output, and you would have the output go out, and then, oops, yeah, back into the filter. And what that is that it's called FB, or yeah, feed. Oh my goodness, feed back, right? Overdrive, right? Overdrive, and then yeah, feedback, if you can read that. So we're feeding back into the filter as opposed to driving the filter. And holy moly, once we get into that, you're gonna freak out. We'll use a combination of overdriving and feedback. We'll use them together, and you can imagine what kind of awesome sounds this can create. This will give your synth sounds basically attitude. You know how like the synths so far we've been making are like, I don't know, the sounds aren't that impressive sounding. It's like, how do I make it sound like, I don't know, Martin Garrix or whatever we're doing these days? How do you do that? Well, that is with using analog model filter designs that react to overdriving and feedback. Exceptionally important stuff there. So let's quickly kind of go over what these mean. So clean is clean. Clean is we should know clean. Clean is essentially easy to grasp, right? It's just digital, right? OSR. What's OSR? Well, OSR is based on the Oscar, right? Okay, so I am not affiliated with Ableton Live in any way. I'm not. I don't even know what it's called when you're an authentic trainer. It's called something. Anyway, I'm not that, and they don't say this. This is my opinion, kind of, but it's very well understood. This is not the view of Ableton Live. I just want to say this, but the OSR circuit type is based on the Oscar synth, which was made in 1983. Right, this is a mono synth. It was one of the first to have MIDI, and only 2,000 were made. So the filter consists of two 12 dB per octave analog filters that could be combined into either a 24 dB low pass or band pass, and such designs of the filter, like the circuitry, were used in the Roland Jupiter 6, which was kind of legendary. But there was a separation control that allowed separate cutoff frequencies of both of the filters. So that's what the OSR is. And essentially, I guess how it works is the order of it goes from clean to analog modeled, kind of cleanish, and then kind of dirty analog. I don't know how to explain it, but it goes in order of aggressiveness or color, I should say. Anyway, so OSR, really good. My nose is itchy. The reason why my nose is itchy is because I talk into the mic really closely, and then the steam tickles my nose hairs. Now you cannot unthink that. Okay, so next up is the MS2. So this is allegedly based off of the Korg MS-20. So this is the MS-20. It was the cool patchable synthesizer made in 1978. It had a really interesting and aggressive filter. Like that. That sounds pretty darn aggressive, hey? Right? All that color, like this is exaggerated, but all that color, you have that, it combines together, and you get a fuller sound. You wouldn't have it like extreme, but if you have enough of these, it really adds to it. So that's the MS2. I'd like to also point out, exceptionally important, that there were two revisions of the MS20. Where is that? Filters. Yeah, there are two filters in the series. Oh, so the original filters were a proprietary IC, so like an integrated circuit, so like a chip. These are too small to see. Right, that's a chip right there, right? So everything was done within the chip, and later they switched to off-the-shelf OTAs, which is kind of like an op amp, but not really. So there's two revisions, so two different characteristics of sounds, and the drop has both emulated, but the MS2, so there's MS1 and MS2. We only have MS2. MS2 is more of a usable and familiar filter design, right? This emulates the circuitry that's in those things, right? You can get a really cool sound. Next up is SMP. And SMP, as far as I know, it's a hybrid between the MS2 and the PRD, right? So it's a mixture between these two. It's taking kind of the best of both worlds, and this is bringing it up to modern, I guess, usability and modern production, and it's a really interesting sound. And this is just a testament to Cytomic's way of Cytomic's contribution to audio making software. Right. Right, let's take a listen to that. Right, what does that sound like? Right, gives it a really cool sound, and that is the SMP. Last is the PRD. Notice how it changes? Right, so yeah, the analog, each one had its own separate characteristics, even how it cuts off, and even how it behaves when the resonance is boosted and things like that. I also want to point out something. So all of these analog modeled, what are they called? Circuit types will emulate so closely to the original hardware that they also self-oscillate, right? So if I go and I boost the resonance past 100, and I just hit play for a second because it auto-mutes, it will go into self-oscillating mode, and this is what those original filters, what they do. It gets into like this feedback mode where it just keeps on. It has to do with how the circuitry behaves. I'm not going to show you a circuit simulation, but it's very accurate. Right, and you get a really cool sound that way if you want, and that's just a high resonance, which is faithful and accurate to how the actual hhardware behaved. So the PRD is the Moog Prodigy, and this is that famous Moog ladder filter, and it's emulated in this as well, used by everyone. It's, yeah, when you think of analog filters, you think of the Moog, and this is Moog Prodigy, which is essentially, based off everything they did before. It's 12 dB per octave. Right? Notice how it just gives it just a lot of attitude and buttocks, I guess. I don't know how you want to call it. I call it buttocks. Anyway, so there's that, and that would be, your first kind of foray into understanding analog modeled filters, and they're all pretty great, and they'll add to your sound. So let's move on to some things I didn't actually cover, but we can go over it really quickly because we should be confident in this. Let's look at the LFO and the LFO / sample and hold. We have essentially something that will automatically move the filter back and forth through this this control here. And, I have this drawing program. I'll just do it. So there's that right there. This will control movement over time. And I'll give it a play. Right. 0.11 hertz. I can move that, around 1 hertz, which will 1 cycle a second. And then the amount, which is the depth, how strong that will oscillate. Right, and that is based on time, not by tempo. We can set it to time and tempo. You notice that new things pop up. We can do that. We can set it to 16ths. Right, and the shape will dictate kind of the movement of what is occurring. We have a number of different shapes here. We have, sine, square, which is essentially up, down, instantaneous. Triangle, which is a different vibe than the sine. Also, you'll notice that the when we select notch or bandpass, the drive will disappear and we'll go back to clean. These don't operate. The math and all that fun stuff, I'm assuming, will not allow it to operate in these modes. These analog filters would not work in these modes. It's kind of like using relativity to find out what's happening inside a black hole. Doesn't really work. Right. We can select the phase. We can shift the phase. Right. And that's good for kind of stereoizing the sound. A lot more apparent with this shape here. And the offset will actually shift where the shape is. So it will, right? So the shape, this triangle, right, is when it's offset at 0 degrees. It basically it's on time every sixth, right? So every sixth it will, it will always kind of start at this. We can tell by that shape, right? So that will be, every sixth it will do that. If we apply an offset, right, in terms of degrees, right, between here and here that would be, 360 degrees, right? This is really, really cool refresher for everyone. So right in the middle, what would that be? We all used to skateboard. 180 degrees, right? So that's where that would be. Degrees would be, it's just a way of measuring distances between kind of timestamps and things like that. So what that would do is that would essentially shift that over, actually. Yeah. I can do this, no big deal. It will actually shift that over to be in the center of where it would be if it's shifted 180. That makes sense. So let's do that. I will clear, put my pen away. Let's do that. And yeah, we'll just set the phase to 0, 0, so they're aligned. Right? Not as obvious, but you can, if you kind of listen to the original. And I'll set this to something divisible. Right, so that's 180. Right, and for the sake of like continuity in your track and like not weirding things out, you want to, you know, a lot of the time you want to be 180. It's just kind of consistent, but you can offset it a tiny bit. It can sound cool. Right, and you can get some cool swing in there as well. Really nice. So there's that. And one thing I didn't cover, this would be the noise shapes. So this is a select kind of a random-ish noise, and then this down here would select another one. What are they? Different sawtooth, sawtooth down, and noise. What are these? I want to know what these are. Oh, okay. So this would be, you know, different sample and hold as per the left and right channel. Right, because there's no offset that you can have in there. And if you're unsure of what sample and hold is, I'll just do it. So sample and hold. Well, sample and hold has the basis in noise. Noise is just, oh no, I'm not gonna have that one. Let's look at some. Let's just pretend that this is noise. It's just random, right? Randomized stuff over time. So what sample and hold does is obviously, you know, this peak is different than this peak, right? So it will essentially separate into grids, right? Depending on what the rate is, the rate will dictate this grid, and it will just pick a random value and then hold it. So yeah, it'll just hold that, hold that, hold that. It'll just do that, right? And then, you know, that's a big one, but whatever. Yeah, it'll just sample at every one sample point and then just hold it. And yeah, it's just randomness, if that makes any sense. And yeah, it's what R2D2, the sound of R2D2, essentially. Really cool. So there's that. One thing I gotta go over, yeah, I wrote down, I didn't go over notch and morph. So this would be notch here. So notch is a really cool effect. Notch can be in clean or OSR, right? So some circuit types, I want to say algorithms because that's kind of what they are, but some circuit types will allow for these kinds of filter types, right? So yeah, OSR works for band and PRD. Yeah, so yeah, high pass, low pass, things like that. OSR for band pass and clean, and then OSR for this. So OSR, yeah, that would work well. Because if we go back, the Wikipedia page says that it consists of two 12 dB per octave analog filters, and they can be combined and moved around in band passy sort of ways. It's really neato filter. But the cool thing about notch filters is back in the day, synths didn't really have phasers. Phasers costed a lot in terms of processing power and things like that. So we would use these notch filters to create a phaser effect. Right? So when you're going for a sound, like an old school sound, that's kind of phasery, but you can't figure it out. It's not a phaser, it's a notch. And next up is this guy right here. This is the Morph Filter. So this is a bunch of filters put in one. The Oberheim, I don't know if I'm pronouncing Oberheim. That synth, the synth from Van Halen Jump, the Oberheim, it had a filter like this, the OSR, and you have the filter cutoff and the resonance, right? But you have this morph here, so you can go from low pass to band to high pass to notch to low pass again. Wow, wow, right? And this just freedom in this this filter morphing. So this is a morph filter or a state variable filter. And that's fun. It does some cool stuff. So that's that, and that gives you, the flexibility to, do a bunch of things and enjoy yourself. So next up is this quantize and this envelope section here. So the envelope will essentially, you know how the LFO was moving this over time, right? The envelope here will duck or raise the cutoff depending on what's being fed into it. So it's reactive to the sound that's affecting it. So what happens is it basically does that with the envelope. So this is the envelope amount. Right, so it's going up. I can also have it kind of go down. Oh, I have quantize on, oops. And the attack and release will dictate the reactiveness of it. And this was used in a lot of disco house and French house tracks. Right, so there's movement. But you really gotta play around with it, because then you'll get it. Right. So when the envelope is down, the filter's moving in the leftmost direction. When it's up, it is opening in the right direction. Right? So it's kind of chaotic. What if we wanted to actually quantize this? Well, this is the quantize button. Right? And it quantizes it, and it makes it more musical. Right? It's just another way to get movement in your tracks here. Right, so with the quantize off, it's kind of like wibbly wobbly, wow, 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 right? Quantize on, it quantizes it to the beat, and these numbers are confusing. It's like, what does this mean? Well, it's based on sixteenths, right? So right now it's 1, right? So 1/16th. Right? We should know. If it's 2, right, we will have that as, 2/16th, which is actually 1/8. And, we go up to, we'll go like 8/16ths. That will be 1/2, right? And then, 16/16ths would be 1. And that'd be 1 bar, right? So that's how you kind of do that. And kind conversely or inversely or whatever you want to say, 0.5/16, that would be 1/32, right? So yeah, just it's an easy way to cram a bunch of information in there. And yeah, it's kind of tricky for people who don't know math or who aren't good at math like me. But yeah, that's essentially it. So, you have your usual, 16ths, and then you'll have your eighths, and then you'll have your the 4/16, that'd be your quarter right there, and then you'll have your half, and then you'll have your bar, right? And then, the other ones would be like your other standard ones. So yeah, you just kind of go through that. Should be pretty well understood. Math isn't necessarily necessary, but yeah, that's essentially what's going on there. Also, this is bothering me. I can't. This is 16ths. Okay, so there we go. The time divisions of this guy right here is explained. That's essentially everything for this video. And yeah, I hope you enjoyed. I hope you learned stuff. Take care, and I'll see you in the next video.